The great red spot churns with the fury of 3 Earths, its crimson eye staring across the void like some ancient unblinking god. For over 400 years, this storm has raged in Jupiter's atmosphere, a hurricane that could swallow our entire world and barely notice the meal. Below its roiling clouds, pressures mount that would crush diamond into dust, while temperatures soar hotter than the surface of Venus. This is Jupiter as we know it, the king of planets, shepherd of asteroids, gravitational giant that shapes the very architecture of our solar system. But Jupiter harbours a secret written in its core, a truth so profound it changes everything we think we know about our cosmic neighbourhood. Deep beneath those hypnotic bands of ammonia and methane, past the metallic hydrogen that flows like liquid metal under impossible pressures, lies Jupiter's heart. Here, crushed into a sphere smaller than Earth, yet containing more mass than all the other planets combined, rests the evidence of what almost was. The core temperature reaches 20,000 Kelvin, hotter than the surface of our Sun. For a moment, let that sink in. The failed planet we call Jupiter burns with an inner fire that exceeds the star that gives us life. This is no accident of physics. This heat represents the dying echo of a cosmic near miss, the fading signature of a process that came tantalizingly close to igniting. Jupiter, the planet we've known for millennia as a wandering star in our night sky, almost became exactly that, a star. The margin of failure was breathtakingly narrow. Had Jupiter accumulated just 75 times more mass during the chaotic birth of our solar system? A cosmic sneeze in terms of the available material swirling through the primordial disk. Nuclear fusion would have sparked in its core. Deuterium would have begun fusing with hydrogen, releasing the sustained energy that marks the boundary between planet and star. Our solar system would have transformed from its current single-star architecture into something far more complex and dangerous. A binary system with 2 suns locked in an eternal gravitational dance. Consider what this means. For 4.6 billion years, Jupiter has existed as astronomy's greatest what-if. Every time you look up at that bright dot moving slowly against the stars, you're witnessing the shadow of an alternate reality that came within a cosmic hair's breadth of existence. The same gravitational forces that today shepherd comets and protect Earth from asteroid impacts might have instead spawned a second sun, bathing our world in the complex rhythms of binary illumination. The implications cascade through every aspect of existence. In a binary star system, Earth's orbit becomes a 3-body problem, one of the most notoriously unsolvable puzzles in celestial mechanics. Instead of our stable, nearly circular path around a single sun, our planet would have wobbled through space influenced by 2 massive gravitational wells, each pulling and tugging according to their own orbital dance. Some years might have brought us closer to both stars, creating hellish greenhouse conditions that would have boiled away our oceans. Other years could have flung us into the outer darkness between the 2 suns, freezing our world into a ball of ice that would make the worst ice age look tropical. The seasons we take for granted, spring's awakening, summer's abundance, autumn's harvest, winter's rest, would have become meaningless concepts in a world where stellar geometry dictated climate more than axial tilt. Instead of the predictable 365-day year that has governed life on Earth since its beginning, we might have experienced decades-long summers followed by generations of winter, or chaotic patterns where the length of a year itself varied dramatically based on the complex orbital mechanics of 3 massive bodies locked in gravitational combat. But the transformation would have reached far deeper than climate and seasons. The very formation of our planetary family would have unfolded along entirely different lines. The asteroid belt, that cosmic junkyard between Mars and Jupiter that today provides a protective barrier and occasional threat, might never have formed at all. Instead, the material that became those rocky fragments could have been captured by one of our 2 suns, or flung out of the solar system entirely during the chaotic early epochs when Jupiter's stellar twin was still consuming mass and growing toward full ignition. Mars, that rust-coloured world that tantalizes us with evidence of ancient water and the possibility of past life, might have ended up as a moon, orbiting one of the binary stars, tidally locked and baked sterile on one side while frozen solid on the other. Venus, already a hell world in our current reality, could have become something even more extreme, or perhaps in some configurations might have evolved into a second Earth-like world, its current runaway greenhouse effect prevented by the complex orbital dynamics of the binary system. The Moon itself, that faithful companion whose gravitational pull drives our tides and stabilizes our axial tilt, creating the stable climate patterns that allowed complex life to evolve, would the Moon even exist in a binary star system? The formation of our natural satellite, believed to have resulted from a Mars-sized object colliding with the early Earth, would have unfolded under entirely different gravitational conditions. Perhaps the debris from such a collision would have been scattered across space instead of coalescing into the Moon. Perhaps Earth would spin wildly on its axis without lunar stabilization, creating climate chaos that would have prevented the emergence of complex life entirely. And what of life itself? Every organism that has ever drawn breath on this planet, from the first primitive bacteria that learned to harvest sunlight 3.5 billion years ago, to the complex multicellular creatures that populate our world today, exists because of Jupiter's failure to ignite. The biochemistry of photosynthesis, evolved over billions of years to capture energy from a single stable sun, would have faced the impossible challenge of adapting to binary illumination. The delicate balance of atmospheric chemistry that allows liquid water to exist on Earth's surface would have been subject to the complex heating and cooling cycles imposed by our wandering path between two stars. The story of evolution on Earth has been shaped by mass extinctions and rapid diversifications, by ice ages and warm periods, by the slow drift of continents and the occasional impact of asteroids or comets. But all of these dramatic events played out within the stable framework of a single sun providing consistent energy input over geological time. Remove that stability, introduce the chaos of binary stellar dynamics, and the entire narrative of life on Earth becomes unrecognizable. Yet perhaps the most unsettling aspect of this cosmic near miss is how close it actually came to reality. Jupiter didn't fall short of stellar ignition by some vast margin that would let us sleep soundly, knowing such a scenario was always impossible. The gravitational dynamics of the early solar system, the distribution of mass within the primordial disk of gas and dust from which our planetary family formed, the timing of various accretion processes, all of these factors came together in a configuration that left Jupiter tantalizingly close to the threshold of star formation. Recent research has revealed just how narrow this margin truly was. Computer simulations of solar system formation show that small variations in the initial conditions, slightly different densities in certain regions of the primordial disk, minor changes in the timing of Jupiter's formation, subtle alterations in the migration patterns of the gas giants, could easily have pushed Jupiter across the line into stellar ignition. We exist in what might be called the Goldilocks zone of solar system architecture. Not too much mass accumulated by Jupiter to create a chaotic binary system, not too little to allow it to serve as the gravitational anchor that brought stability to the outer solar system. The implications extend far beyond our own cosmic backyard. As we discover exoplanets throughout the galaxy, we're finding that binary star systems are remarkably common, perhaps even more common than single-star systems like our own. Many of these binary systems do indeed host planets, worlds that experience the complex orbital dynamics and variable illumination that Earth would have faced had Jupiter succeeded in its stellar ambitions. Studying these distant worlds gives us glimpses into the alternate reality that might have been our fate, windows into the cosmic path not taken. Standing beneath Jupiter's glow in our night sky, knowing what we now know about its near-stellar nature, creates a profound sense of cosmic vertigo. We are the products of an astronomical near miss, beneficiaries of a failed star that shaped everything from our planet's climate to the evolution of consciousness itself. Every sunset you've ever watched, every season you've experienced, every breath of oxygen produced by plants harnessing the light of a single stable sun, all of it exists because Jupiter fell just short of ignition. But to understand what we lost, or what we were spared, we must journey back 4.6 billion years to the violent birth of our solar system, where the forces that nearly gave us a second sun first began their cosmic dance in a swirling disk of gas and dust that would determine the fate of every world we've ever known. 4.6 billion years ago, where our solar system now resides, There was nothing but darkness punctuated by the cold glitter of distant stars. No planets, no asteroid belt, no comets tracing elegant arcs through the void, only a vast molecular cloud of gas and dust drifting through the galaxy's spiral arm like cosmic fog. This nebula stretched across dozens of light years, its density so low that it barely registered above the vacuum of space itself. Yet within this seemingly empty expanse lay the raw materials for everything we know: hydrogen, helium forged in the Big Bang, heavier elements cooked in the nuclear furnaces of dying stars and scattered into space by supernovae. The transformation began with violence. Somewhere in our galactic neighbourhood, a massive star, perhaps 50 times more massive than our current Sun, reached the end of its stellar lifetime. In its final moments, this giant exploded with the force of 10 billion suns, sending a shockwave racing outward at thousands of kilometers per second. When this expanding wall of superheated gas slammed into our quiet molecular cloud, it compressed the diffuse material, creating dense pockets where gravity could finally gain purchase. What had been spread thin across the vastness of space began to collapse inward, drawn together by the inexorable pull of its own mass. As the cloud contracted, conservation of angular momentum, the same principle that makes a figure skater spin faster when she pulls in her arms, caused it to rotate faster and faster. The collapsing material flattened into a disk, with most of the mass concentrating toward the center where gravitational forces were strongest. At the heart of this swirling maelstrom, temperatures and pressures began to climb as hydrogen atoms were crushed together with ever-increasing force. This was the birth of our proto-sun, though it would be millions of years before nuclear fusion would ignite in its core and transform it into the stable star we know today. But the proto-sun was not alone in its gravitational feast. Throughout the disk, smaller concentrations of material began their own collapse, seeded by turbulence and density fluctuations within the swirling gas and dust. One of these secondary concentrations, located roughly 5 times farther from the center than Earth's eventual orbit, was destined to become Jupiter. And from the very beginning, this future giant was locked in a cosmic race with its stellar parent, a race that would determine the architecture of our entire solar system. The early stages of this competition were fierce and chaotic. Both the proto-Sun and proto-Jupiter were gravitational vacuum cleaners, sweeping up material from their surrounding regions with insatiable hunger. But they operated under different rules. The proto-Sun, blessed with its central position where material density was highest, could draw from the richest feeding ground in the disk. Proto-Jupiter, relegated to the outer reaches where the pickings were leaner, had to work harder for every gram of mass it could accumulate. Yet Jupiter possessed a crucial advantage that nearly compensated for its peripheral location. It formed in the region where water could freeze, beyond what astronomers now call the snow line, roughly where the asteroid belt sits today. Temperatures were low enough for water vapor to condense into ice crystals. This might seem like a minor detail, but it fundamentally altered the planet-building process. Solid ice particles provided much more efficient building blocks than the gas and microscopic dust grains available in the inner solar system. Proto-Jupiter could grow by accumulating these icy planetesimals, building up a solid core that became massive enough to gravitationally capture the hydrogen and helium gas that made up the bulk of the disk. The critical threshold for this runaway gas accretion was approximately 10 Earth masses. Once Jupiter's solid core reached this size, its gravitational field became strong enough to hold onto the light gases that were constantly trying to escape into space. From that moment forward, Jupiter's growth accelerated exponentially. It began devouring gas directly from the disk, ballooning in mass at a rate that alarmed the gravitational stability of the entire system. Current models suggest that Jupiter reached perhaps 10 times its present mass during this early feeding frenzy, roughly equivalent to 3,000 Earths worth of material. At this colossal size, it wasn't merely a planet anymore, but something approaching a failed star. Its core temperatures soared as gravitational compression heated the accumulated gas to thousands of degrees. Had it continued growing at this rate for just a few million more years, it would have achieved the mass necessary for deuterium fusion, the first step toward true stellar ignition. But Jupiter's ravenous appetite began to work against it. As it consumed more and more material from its orbital zone, It also gravitationally perturbed the paths of nearby planetesimals, either flinging them into the outer solar system or sending them spiraling inward toward the Sun. This disruption reduced the available material for further growth, gradually starving the giant of the resources it needed to reach stellar masses. More dramatically, Jupiter's enormous gravitational influence began to reshape the entire disk structure. The giant planet carved out gaps in the material around it, creating zones of depletion that extended far beyond its immediate vicinity. These gaps affected the flow patterns of gas and dust throughout the system, altering the accretion rates of all the forming planets. Most critically, Jupiter's gravitational torques began to affect its own orbit, causing it to migrate inward toward the Sun. This inward migration, a process astronomers call Type II migration, nearly spelled disaster for the inner solar system. Computer simulations show that the early Jupiter spiraled inward at an alarming rate, possibly reaching as close as 1.5 astronomical units from the Sun, closer than Mars orbits today. Had this migration continued unchecked, Jupiter would have ploughed through the regions where Mercury, Venus, Earth, and Mars were still forming, either ejecting these smaller worlds from the system entirely or causing them to spiral into the Sun. The salvation of the inner planets came from an unexpected source: Saturn. As the second gas giant began its own rapid growth phase, it too started migrating inward under the gravitational torques of the disk. When Saturn reached a specific orbital resonance with Jupiter, likely a 2:3 ratio where Jupiter completed 2 orbits for every 3 of Saturn's, the gravitational dynamics changed dramatically. Instead of both planets continuing their inward death spiral, they began to migrate outward together, retreating to the outer solar system and leaving the inner regions relatively undisturbed. This remarkable turnaround, known as the Grand Tack model, may have saved Earth's existence. The name comes from sailing terminology, describing how Jupiter tacked like a sailboat, reversing its direction when the gravitational winds changed. During its brief sojourn in the inner system, Jupiter had scattered most of the planetesimals that would have built Mars into a larger planet, explaining why the red planet is so much smaller than Earth and Venus. But the giant's retreat allowed the scattered debris to reaccumulate into the terrestrial planets we know today. The Grand Tack also had profound implications for Jupiter's stellar ambitions. The outward migration carried Jupiter away from the dense inner regions of the disk, where material was most abundant. As it moved into the sparser outer regions, its growth rate slowed dramatically. The window for achieving stellar masses was closing, constrained by both the reduced availability of raw materials and the ongoing evolution of the disk itself. The disk was aging rapidly during these crucial epochs. The proto-sun's luminosity was increasing as it contracted toward the main sequence, and the stellar winds it generated began to drive away the remaining gas. This process, known as disk dispersal, typically occurs within the first 10 million years of a star's formation. Once the gas was gone, Jupiter's opportunity to grow through direct accretion would end forever. The race between Jupiter's growth and disk dispersal came down to a matter of timing measured in cosmic heartbeats. Had Jupiter formed just a few million years earlier, when more material was available, it might have achieved the critical mass for stellar ignition before the disk dissipated. Had Saturn's formation been delayed, preventing the Grand Tack reversal, Jupiter might have continued its inward migration long enough to access the denser material closer to the Sun. Instead, Jupiter found itself caught in a gravitational catch-22. Its enormous mass made it the dominant gravitational influence in the outer solar system, but that same mass had disrupted its own feeding ground, limiting its ability to grow further. By the time the disk began its final dispersal phase, Jupiter had settled into a configuration that left it tantalizingly close to, but ultimately short of, the mass needed for stellar ignition. The exact margin of this failure continues to be refined by astronomical observations and theoretical models. Recent studies of Jupiter's interior, informed by data from the Juno spacecraft, suggest that the planet's core is less dense and more diffuse than previously thought. This finding implies that Jupiter may have undergone a more complex formation process, possibly involving the collision and merger of the multiple planetary embryos in its early history. Such collisions would have released enormous amounts of energy, heating Jupiter's interior and potentially bringing it even closer to the conditions needed for stellar ignition than previously realized. The isotopic composition of Jupiter's atmosphere also provides clues about its near-stellar past. The ratio of deuterium to hydrogen in Jupiter's outer layers is nearly identical to that of the primordial solar nebula, suggesting that the planet never became hot enough in its interior to significantly alter these ratios through nuclear processing. Yet the very fact that Jupiter contains detectable amounts of deuterium, an isotope that would be consumed in the first stages of stellar ignition, hints at how close it came to crossing that threshold. As the disk dispersal reached its final stages, Jupiter began the long process of settling into its current configuration. The intense heat generated by its formation period gradually radiated away into space, though this cooling process would take billions of years. The gravitational compression that had brought Jupiter so close to stellar ignition became the source of the internal heat that the planet still radiates today. More energy than it receives from the Sun, a reminder of its unfulfilled stellar potential. The formation of Jupiter's magnificent system of moons occurred during this cooling phase, as the planet shed its excess angular momentum and settled into a more stable configuration. The four largest moons, Io, Europa, Ganymede, and Callisto, formed from a disk of material orbiting the proto-Jupiter, much like a miniature version of the solar system itself. Had Jupiter achieved stellar ignition, these worlds would have become planets orbiting a binary star system, their surfaces sculpted by the complex interplay of two stellar sources of heat and light. But perhaps the most profound legacy of Jupiter's failed stellar evolution lies in what it made possible elsewhere in the solar system. By falling just short of ignition, Jupiter remained in the outer solar system as a gravitational shepherd, its immense mass serving as a cosmic vacuum cleaner that swept up potentially dangerous asteroids and comets before they could threaten the inner planets. Its gravitational influence also stabilized the orbits of the other gas giants, creating the orderly arrangement of outer planets that has persisted for billions of years. The nitrogen-rich atmosphere of Titan, the subsurface oceans of Europa and Enceladus, the complex ring systems of Saturn, all of these wonders exist because Jupiter's stellar ambitions fell short. Had the gas giant succeeded in its quest for ignition, the intense radiation and stellar winds from a second sun would have stripped away the delicate atmospheres and volatile compounds that make these worlds so fascinating to explore. As we trace the story of our solar system's formation, Jupiter's near miss with stellar ignition emerges as perhaps the most consequential single event in determining the character of our cosmic neighbourhood. The difference between the solar system we inhabit and the chaotic binary system we might have known came down to a cosmic roll of the dice played out over the course of just a few million years in our system's earliest epochs. But the implications of this alternate history extend far beyond the rearrangement of planetary orbits and the reshuffling of celestial mechanics. Had Jupiter succeeded in its stellar evolution, the very concept of habitability within our solar system would have been redefined in ways that challenge our understanding of how life emerges and persists in the universe. Locked in a gravitational embrace that brings them as close as the distance from the Sun to Uranus, swing around their common centre of mass every 80 years. Their third companion, the red dwarf Proxima Centauri, orbits this binary pair at a distance so vast it takes over 500,000 years to complete a single revolution. This is our nearest stellar neighbour, and a window into the alternate reality that Jupiter's stellar ignition would have created. But Alpha Centauri, for all its proximity and familiarity, represents just one possible configuration of binary star systems. Had Jupiter achieved stellar ignition in our own system, the gravitational architecture would have been far more complex and dramatically more dangerous for any worlds caught in its influence. Picture instead a binary system where the two stars orbit much closer together, their gravitational dance measured not in decades but in years or even months. This is the scenario that Jupiter's transformation would have likely produced. Two massive bodies, one roughly the size of our current Sun, the other perhaps 75 times Jupiter's actual mass, locked in a tight orbital embrace that would have fundamentally rewritten the laws of planetary formation and survival. In such a system, the very concept of stable planetary orbits becomes a nightmare of celestial mechanics. Unlike our current solar system, where planets follow predictable elliptical paths around a single gravitational anchor, worlds in a tight binary system must navigate the constantly shifting gravitational influences of two massive objects. The mathematics of this three-body problem, predicting the motion of a planet under the combined gravitational pull of two stars, is so complex that no exact analytical solution exists. Each planetary orbit becomes a unique dance of attraction and repulsion, stability, and chaos. Computer simulations reveal that only certain orbital configurations can remain stable over astronomical timescales in such systems. Planets can survive in close orbits around one star or the other, provided they stay well within that star's gravitational dominance zone. Alternatively, worlds can maintain distant orbits around both stars, circling the entire binary system at distances where the two stars appear as a single gravitational unit. But the intermediate zones, the regions where Earth currently resides in our single-star system, become gravitational no-man's lands where stable orbits simply cannot exist. The implications for Earth's existence in such a system are profound and disturbing. Our planet's current orbit, at 1 astronomical unit from the Sun, would place it squarely in the chaotic intermediate zone where long-term stability is impossible. Earth would face 3 possible fates: ejection from the solar system entirely, collision with one of the binary stars, or migration to one of the few stable orbital zones that could support planetary motion. If Earth somehow managed to achieve a close orbit around our original Sun, the equivalent of Mercury's current position or even closer, it would become tidally locked, with one hemisphere permanently facing the star while the other remained in eternal darkness. The day side would be a hellscape of molten rock and vaporized oceans, while the night side would be frozen solid, creating temperature differentials that would drive atmospheric circulation patterns unlike anything we can imagine. The narrow twilight zone between these extremes might theoretically support some forms of life, but the complex chemistry that led to our planet's rich biosphere would never have had the chance to develop. Alternatively, Earth might have been captured into a wide orbit around both stars, circling the entire binary system at a distance of perhaps 10 or 20 astronomical units, farther out than Jupiter currently orbits the Sun. In this configuration, our planet would receive energy from both stellar sources, but the complex orbital mechanics would create wild variations in the amount of heat and light reaching Earth's surface. Instead of the stable 365-day year that has governed our climate for billions of years, Earth's orbital period might stretch to decades or centuries, with corresponding variations in seasonal patterns that would make the ice ages look like minor climate fluctuations. The gravitational interactions between the binary stars would also create tidal forces on Earth far more extreme than anything we experience from the Moon's influence. These stellar tides would flex and squeeze our planet's crust, generating continuous geological activity that would make the Ring of Fire look like a minor inconvenience. Massive earthquakes and volcanic eruptions would be constant features of the planetary surface, preventing the formation of stable continents and making the emergence of complex life forms extraordinarily unlikely. But perhaps the most dramatic difference would be the absence of the asteroid belt as we know it. In our current solar system, this debris field between Mars and Jupiter serves as both a protective barrier and a source of occasional threats to the inner planets. The asteroids represent material that never coalesced into a planet, prevented from doing so by Jupiter's gravitational interference. In a binary star system, this region would have been subjected to far more complex and violent gravitational perturbations. The resonance zones, regions where orbital periods create simple mathematical ratios with the binary star's revolution, would become cosmic woodchippers, grinding up any solid material that wandered into them. Instead of a relatively stable asteroid belt, the space between the inner and outer regions of the solar system would be filled with a chaotic swarm of debris, much of it on highly elliptical or even hyperbolic trajectories that would carry rocks and ice balls throughout the system. This debris would pose a constant bombardment threat to any surviving planets. The late heavy bombardment that scarred the Moon and early Earth roughly 4 billion years ago would be replaced by a continuous rain of impacts that never ceased. Any atmosphere that a planet managed to retain would be constantly stripped away by the kinetic energy of incoming projectiles. Ocean formation would be nearly impossible, as water would be vaporized by impacts faster than it could condense and accumulate on planetary surfaces. Mars, already a smaller and more vulnerable world than Earth, would likely have been ejected from the system entirely during the chaotic early epochs, when the binary stars were still settling into their final configuration. The red planet's current orbit places it in a region that would have been particularly unstable in a binary system, subject to gravitational perturbations from both stars that would have gradually increased the eccentricity of its orbit until it either collided with the inner planets or was flung into interstellar space. The fate of Venus would depend critically on the exact configuration of the binary system. If it managed to achieve a close orbit around the primary star, Venus might have become an even more extreme version of the hell world we know today, baked by the combined radiation of two stellar sources and subject to complex tidal heating that would have melted its surface into a permanent ocean of lava. Alternatively, Venus might have been captured by the secondary star, our transformed Jupiter, creating a unique world heated by stellar radiation on one side and the infrared glow of a brown dwarf companion on the other. The outer planets would have faced their own existential challenges in a binary star system. Saturn, currently Jupiter's gravitational partner in shepherding the solar system's architecture, would have found its formation process completely disrupted by the presence of a second star in the inner system. The delicate balance of conditions that allowed Saturn to form its magnificent ring system would have been upset by the complex tidal forces and radiation environment created by binary stellar dynamics. Uranus and Neptune, those distant ice giants that currently define the outer edge of our planetary system, would have been subject to gravitational perturbations that could have ejected them from the system entirely, or sent them on highly elliptical orbits that would carry them alternately close to and far from the binary pair. Their extensive moon systems, including worlds like Titan with its thick nitrogen atmosphere and methane lakes, would have been stripped away during close approaches to the central stars. Perhaps most tragically, the formation of the Kuiper Belt and Oort cloud, those vast reservoirs of comets that surround our solar system like a spherical shell, would have been prevented entirely. These regions contain the pristine materials left over from the solar system's formation, frozen archives of the conditions that existed during our system's birth. In a binary star system, the gravitational perturbations would have scattered this material throughout the galaxy, depriving us of both the beautiful cometary displays that grace our skies and the scientific insights these primordial objects provide about our cosmic origins. The very concept of seasons would have been revolutionized in ways that challenge our understanding of planetary climate systems. Instead of the predictable cycle of spring, summer, autumn, and winter, driven by Earth's axial tilt, seasonal patterns would be governed by the complex orbital mechanics of the binary star system. A planet might experience decades of continuous summer when its elliptical orbit carried it close to both stars simultaneously, followed by equally long winters when it swung out to the farthest reaches of its trajectory. More disturbing still would be the possibility of chaotic seasonal variations with no predictable pattern at all. The gravitational interactions between the binary stars and any surviving planets could create orbital resonances that would cause dramatic changes in planetary orbits over relatively short timescales. A world might enjoy stable, Earth-like conditions for thousands of years, only to be suddenly perturbed into a highly elliptical orbit that would alternate between furnace-like heat and interstellar cold. The magnetic fields that protect planets from stellar radiation would also be affected by the complex electromagnetic environment of a binary star system. Our Earth's magnetosphere, generated by the motion of molten iron in our planet's core, creates a protective bubble that deflects the charged particles streaming from the Sun. In a binary system, planets would be bombarded by stellar winds from two sources, creating complex interaction zones where magnetic field lines could reconnect and generate enormous bursts of energy that would sterilize planetary surfaces. Even if some worlds managed to maintain stable orbits and retain their atmospheres, the biological implications would be staggering. The complex light cycles created by binary illumination would challenge every aspect of how life develops and evolves. Plants would need to adapt to wildly varying light intensities and spectral compositions as the two stars moved through their orbital dance. The circadian rhythms that govern biological processes in virtually all Earth life forms would become meaningless in a world where the length and intensity of days could vary dramatically, depending on the relative positions of the binary stars. The gravitational environment would also affect the evolution of life in subtle but profound ways. The tidal forces generated by two massive gravitational sources would create stress patterns in planetary crusts and oceans that could either stimulate or inhibit the development of complex ecosystems. Tidal pools, those crucial nurseries where life may have first emerged on Earth, would experience chaotic variations in water level that would prevent the stable conditions needed for early biochemical evolution. Yet perhaps the most unsettling aspect of this binary alternative is how it illuminates the extraordinary sequence of cosmic coincidences that allowed our current solar system to emerge. The precise timing of Jupiter's formation, the exact amount of mass it accumulated before disk dispersal, the gravitational rescue provided by Saturn's formation. All of these factors had to align within narrow windows of opportunity to create the stable, single-star system that became the cradle for life on Earth. As we peer deeper into the galaxy and discover more exoplanetary systems, we're beginning to understand just how rare and precious our current configuration may be. Binary star systems are extraordinarily common throughout the universe, perhaps comprising the majority of all stellar systems. Yet the planets we've discovered in these systems tend to be extreme worlds, super-Earths baked by the combined radiation of two stars, gas giants on wildly eccentric orbits, or distant worlds so far from their parent stars that they receive less energy than Pluto receives from our Sun. The stable, temperate conditions that allowed Earth to develop its rich biosphere may be far more unusual in the cosmic context than we ever imagined. We exist not just because conditions on Earth were suitable for life, but because Jupiter's stellar ambitions fell short at precisely the right moment in our solar system's development. Had that cosmic dice roll landed differently, the story of life in the universe might have unfolded along entirely different lines if it unfolded at all. But to fully grasp the implications of Jupiter's near-stellar transformation, we must examine how it would have affected not just the orbital mechanics of planets, but the very foundations of existence on the world we call home. Imagine standing on the surface of our world in this alternate reality, where Jupiter blazes in the sky as a crimson dwarf star. The familiar rhythm of day and night that has governed life on Earth for billions of years dissolves into something far more complex and alien. As our planet traces its precarious orbit through the gravitational field of two stars, the very concept of a solar day becomes meaningless. Sometimes both stars hang above the horizon simultaneously, their combined radiation baking the landscape with an intensity that would make the Sahara seem temperate. Other times, both stars set within hours of each other, plunging the world into a darkness broken only by their distant glow, creating winters that could last for months or even years. This is not merely a rearrangement of familiar celestial mechanics. It represents a fundamental transformation of the physical processes that make Earth habitable. Every aspect of our planet's behavior, from the circulation of its atmosphere to the dynamics of its magnetic field, would be reshaped by forces that challenge our understanding of what makes a world suitable for life. The gravitational environment alone would be unlike anything in our current experience. Earth would find itself perpetually caught between two massive gravitational wells, each one pulling and stretching our planet's structure with forces that dwarf anything we associate with tidal effects. The Moon's gentle tug, which currently raises our ocean tides by mere meters twice daily, would be overwhelmed by stellar tidal forces operating on scales that would reshape the planet's entire structure. Consider the implications for Earth's solid body. Instead of the relatively stable, spherical shape our planet maintains today, Earth would be constantly deformed by the competing gravitational pulls of its two stellar parents. The planet would be stretched into an elongated ellipsoid, with its longest axis always pointing toward whichever star exerted the stronger gravitational influence at any given moment. As Earth moved through its complex orbital dance, different parts of the planet would experience varying degrees of stretching and compression, generating internal stresses that would dwarf the tectonic forces that drive earthquakes and volcanic activity in our current world. The result would be a planet in constant geological turmoil. The Pacific Ring of Fire, that belt of volcanic activity that currently produces dramatic but relatively localized eruptions, would be replaced by global-scale tectonic chaos. Massive fault systems would crack across continents, driven not by the slow collision of tectonic plates, but by the relentless flexing of the planet's crust under stellar tidal forces. Volcanic activity would be continuous and planet-wide, as the constant deformation of Earth's interior would keep vast regions of the mantle, in a molten state. Mountain ranges would be ephemeral features, thrust up by tidal forces only to be worn down by equally powerful geological processes operating on accelerated timescales. The stable continental platforms that have provided the foundation for complex ecosystems throughout Earth's history would be constantly fracturing and reforming, preventing the development of the long-term geological stability that complex life requires. Ocean dynamics would be revolutionized in ways that challenge our understanding of how water behaves on planetary scales. Instead of the familiar twice-daily tidal cycle driven by lunar gravity, Earth's oceans would be subject to complex tidal patterns governed by the orbital mechanics of two stars. During periods when both stars aligned on the same side of Earth, tidal bulges could reach heights of hundreds of meters, creating tsunami-like conditions that would persist for days or weeks. Conversely, when the two stars pulled from opposite directions, the oceans could be stretched thin across the planet's surface, exposing vast areas of seafloor and concentrating the remaining water into deep basins around the equatorial regions. These extreme tidal variations would prevent the formation of stable coastal environments, where life first emerged on our planet. The intertidal zones that served as evolutionary laboratories for the transition from marine to terrestrial life would be replaced by constantly shifting boundaries between land and sea. No organism could adapt to an environment that changed so dramatically and unpredictably over such short timescales. The atmospheric consequences would be equally profound. Earth's current weather patterns are driven by the relatively uniform heating provided by a single sun, creating predictable circulation cells that distribute heat and moisture around the globe. In a binary star system, atmospheric dynamics would be governed by complex heating patterns that change constantly as the two stars move through their orbital dance. When both stars shine from the same general direction, the day side of Earth would receive an enormous influx of energy that would superheat the atmosphere, driving convective storms of unprecedented violence. The temperature differential between the intensely heated day side and the relatively cool night side would generate atmospheric circulation patterns that dwarf the strongest hurricanes in our current climate system. These superstorms would redistribute heat and moisture around the planet with such force that they would scour the surface clean of any accumulated soil or sediment, preventing the formation of stable ecosystems. During periods when the two stars illuminate different hemispheres simultaneously, Earth would experience atmospheric circulation patterns that have no analogy in our current world. Instead of the familiar global circulation driven by equatorial heating, the planet would be subject to complex thermal patterns that could drive jet streams in multiple directions simultaneously, creating atmospheric turbulence that would make flight impossible for any organism attempting to navigate through the air. The chemical composition of the atmosphere would also be unstable under such conditions. The extreme heating during periods of double illumination would drive photochemical reactions at rates that would rapidly deplete or transform the atmospheric gases that support life. Oxygen, that precious molecule that enabled the evolution of complex life on Earth, would be consumed in oxidation reactions with surface materials heated to extreme temperatures. Water vapor would be photodissociated by intense stellar radiation, with the lightweight hydrogen escaping to space and leaving behind an increasingly dense atmosphere of heavier gases. Earth's magnetic field, that invisible shield that protects us from the charged particles streaming from the Sun, would be disrupted by the complex electromagnetic environment of a binary star system. Our planet's magnetosphere is generated by the circulation of molten iron in Earth's core, driven by the planet's rotation and convective heat transfer. The extreme tidal forces in a binary system would disrupt these circulation patterns, potentially weakening or even eliminating the magnetic field that protects our atmosphere from being stripped away by stellar winds. The electromagnetic environment around Earth would be further complicated by the interaction between stellar winds from two different sources. In our current solar system, the solar wind creates a relatively stable heliosphere around the Sun, a bubble of charged particles that extends far beyond the orbit of Pluto. In a binary system, the interaction between two stellar winds would create complex magnetic field geometries with zones of magnetic reconnection that could generate bursts of high-energy radiation capable of sterilizing planetary surfaces. The Moon, that faithful companion whose gravitational influence has stabilized Earth's axial tilt, and driven the tidal cycles that may have been crucial for the emergence of life, would face an uncertain fate in this binary environment. The complex gravitational field created by two stars would subject the Moon to perturbations that could either send it spiralling into Earth or fling it out of the Earth-Moon system entirely. If the Moon somehow managed to maintain its orbit around Earth, its stabilizing influence on our planet's rotation would be overwhelmed by the gravitational torques exerted by the two stars. Earth's rotational axis would wander chaotically, creating unpredictable variations in the planet's seasonal patterns that would make the Milankovitch cycles, those subtle orbital variations that drive ice ages in our current world, look like minor perturbations. Without the Moon's stabilizing presence, Earth might begin tumbling end over end, experiencing wild swings in axial tilt that would alternately expose the polar regions to intense stellar radiation and plunge the equatorial zones into extended darkness. Such chaotic rotational behavior would create climate variations so extreme that no stable ecosystem could adapt to them. The very concept of seasons, those predictable cycles that have governed the evolution of life on Earth for billions of years, would be replaced by chaotic climate variations driven by the complex orbital mechanics of the binary star system. Instead of the gentle transition from spring through summer to autumn and winter, driven by the 23.5-degree tilt of Earth's rotational axis, our planet would experience climate cycles governed by its position relative to two gravitational and radiative sources. During portions of Earth's orbit, when it passed close to both stars simultaneously, the planet would experience what could only be described as a super summer, a period of intense heating that would vaporize the oceans and create atmospheric temperatures hot enough to melt lead. Conversely, when Earth's complex orbital trajectory carried it to the outer reaches of the system, far from both stellar sources, the planet would plunge into a super winter that would freeze the atmosphere itself, creating snowfall composed of nitrogen and oxygen rather than water. These extreme seasonal variations would prevent the formation of stable ice caps at the poles, those vast reservoirs of frozen water that help regulate Earth's climate by reflecting solar radiation back into space. Instead of the relatively stable ice sheets that have persisted at Earth's poles for millions of years, providing crucial feedback mechanisms that help maintain global climate stability, the polar regions would alternate between being completely ice-free during super summers and frozen solid during super winters. The hydrological cycle, that crucial process by which water evaporates from the oceans, forms clouds, and returns to the surface as precipitation, would be completely disrupted by these extreme climate variations. During periods of intense double illumination, the oceans would boil away entirely, creating an atmosphere so thick with water vapor that the surface would be perpetually shrouded in scalding fog. During superwinters, this atmospheric water would condense and freeze, potentially covering the entire planet in layers of ice several kilometers thick. Such dramatic swings in the global water budget would prevent the formation of stable river systems, those crucial arteries that transport nutrients and sediments across continental surfaces and create the diverse habitats that support terrestrial ecosystems. The great river deltas where human civilization first flourished, the Nile, the Tigris and Euphrates, the Yangtze, could never form in a world where the water cycle itself is subject to chaotic variations on timescales, measured in years or decades rather than seasons. The impact on Earth's carbon cycle would be equally devastating. In our current world, the gradual exchange of carbon between the atmosphere, oceans and geological formations helps regulate global temperatures over geological timescales, preventing runaway greenhouse or icehouse conditions. The extreme temperature swings in a binary star system would overwhelm these regulatory mechanisms, causing massive releases of carbon dioxide during super summers as carbonate rocks decompose under extreme heat, followed by equally dramatic carbon sequestration during super winters as atmospheric carbon dioxide freezes out of the atmosphere. These wild fluctuations in atmospheric composition would create feedback loops that would amplify the already extreme climate variations. High concentrations of carbon dioxide released during super summers would enhance the greenhouse effect, making the hot periods even more intense. The subsequent removal of atmospheric carbon dioxide during super winters would reduce the atmosphere's ability to retain heat, making the cold periods even more severe. perhaps most fundamentally, the complex light environment created by two stars would challenge the very biochemical processes that power life on Earth. Photosynthesis, the process by which plants convert sunlight into chemical energy, evolved over billions of years to operate efficiently under the specific spectral characteristics and intensity of our Sun. The variable light conditions in a binary star system, sometimes too dim, sometimes too intense, often featuring spectral compositions that change as the two stars move through their orbital dance, would make it nearly impossible for photosynthetic organisms to maintain the stable energy production that complex ecosystems require. The foundation of Earth's food web would crumble under conditions where the primary producers, those photosynthetic organisms that convert stellar energy into biological energy, could not maintain consistent metabolic activity. Without stable primary production, the complex food webs that support diverse ecosystems would collapse, leaving only the most primitive chemosynthetic organisms that derive energy from geological processes rather than stellar radiation. As we contemplate the full implications of Earth's existence in such a binary system, a disturbing picture emerges of a world caught between two gravitational masters, subject to forces and variations that would prevent the emergence of anything resembling the stable, life-supporting environment we know today. Yet even this physical chaos pales in comparison to the biological challenges that any potential life would face in attempting to evolve and thrive under such extreme and unpredictable conditions. In the deepest trenches of Earth's oceans, where sunlight has never penetrated and crushing pressures would instantly destroy any surface-dwelling organism, life thrives in conditions that seem utterly alien to our familiar world. Around hydrothermal vents, where superheated water rich in hydrogen sulfide erupts from the seafloor, entire ecosystems flourish without any dependence on photosynthesis. Bacteria harvest energy from chemical reactions, tube worms extend their crimson plumes into the toxic water, and bizarre fish navigate by bioluminescent signals in the eternal darkness. These deep-sea communities represent life's most extreme adaptation to hostile conditions, yet even they would struggle to survive in the chaotic environment of a binary star system. The challenge begins at the most fundamental level of biological organization, the molecular machinery that stores and transmits genetic information. DNA, that elegant double helix that carries the blueprints for all life on Earth, is remarkably fragile when exposed to high-energy radiation. The phosphate bonds that hold the DNA backbone together can be broken by ultraviolet light, X-rays, or energetic charged particles, causing mutations that are usually lethal to the organism. In our current solar system, Earth's atmosphere and magnetic field provide crucial protection from such radiation, filtering out the most dangerous wavelengths and deflecting charged particles from the solar wind. In a binary star system, this protective shield would be constantly overwhelmed. The combined radiation output from two stars would include not only the familiar visible light and moderate ultraviolet that drive photosynthesis, but also intense bursts of X-rays and gamma rays generated when the stellar magnetic fields interact. During periods when both stars flare simultaneously, solar flares from one star triggering magnetic reconnection events in the other, the radiation environment would become so intense that DNA molecules would be shattered faster than cellular repair mechanisms could fix them. The few organisms that might survive such conditions would need to develop repair mechanisms far more sophisticated than anything found in terrestrial life. Some extremophile bacteria on Earth, such as Deinococcus radiodurans, can survive radiation levels that would be instantly lethal to most organisms by maintaining multiple copies of their genome and employing incredibly efficient DNA repair systems. But even these radiation-resistant champions would be overwhelmed by the constant bombardment of high-energy particles in a binary star environment. Any life that did manage to evolve under such conditions would bear little resemblance to the carbon-based biochemistry we know. The complex organic molecules that form the basis of terrestrial life, proteins, lipids, nucleic acids, and carbohydrates, would be constantly broken down by radiation and extreme temperature fluctuations. Instead, life might need to rely on more robust chemical systems, perhaps based on silicon compounds that remain stable at higher temperatures, or metallic complexes that can maintain their structure under intense radiation. The energy production systems that power all known life would face equally daunting challenges. Photosynthesis, the process that captures solar energy and converts it into chemical bonds, evolved over billions of years to operate efficiently under the stable, predictable illumination provided by our sun. The photosystem complexes in plant cells are precisely tuned to absorb specific wavelengths of light, splitting water molecules and using the released electrons to power the synthesis of energy-rich compounds like glucose. In a binary star system, the spectral composition and intensity of available light would be constantly changing. When both stars shine from the same direction, the combined illumination would be so intense that it would overwhelm photosynthetic systems, breaking down the delicate chlorophyll molecules faster than they could be replaced. When the stars illuminate different hemispheres, plants would need to simultaneously process light from two different spectral sources, each requiring different photosynthetic machinery. The temporal variations in light availability would pose an even greater challenge. Photosynthetic organisms require relatively consistent energy input to maintain their metabolic processes and build the complex organic molecules needed for growth and reproduction. The chaotic light cycles in a binary system, sometimes intense double illumination, sometimes extended periods of darkness when both stars set simultaneously, would make it impossible for plants to maintain stable energy production. Instead of the familiar green plants that dominate terrestrial ecosystems, life in a binary system might need to rely on chemosynthesis, the process by which organisms derive energy from chemical reactions rather than sunlight. But even chemosynthetic life would face unprecedented challenges in such an environment. The extreme temperature fluctuations would affect the rates of chemical reactions unpredictably, while the constant geological upheaval would disrupt the stable chemical gradients that chemosynthetic organisms depend upon. The search for life around binary stars in our own galaxy provides sobering insights into the biological challenges such systems present. Kepler 16b, a gas giant planet orbiting both stars of a binary system 200 light-years from Earth, experiences temperature variations so extreme that any solid surface would alternate between being molten and frozen solid. The planet's year lasts 229 days, but the amount of energy it receives from its two parent stars varies by more than 20% as the stars orbit each other, creating climate variations that would challenge even the most adaptable organisms. More intriguingly, astronomers have discovered potentially habitable planets in the Alpha Centauri system, that nearby triple star system that serves as our best example of complex stellar dynamics. Proxima Centauri b, a rocky planet orbiting in the habitable zone of the system's red dwarf component, experiences conditions that illuminate the challenges life would face even in a relatively stable binary environment. The planet is tidally locked, with one side permanently facing its star while the other remains in eternal darkness. Any potential atmosphere would be constantly stripped away by stellar winds and flares from its red dwarf parent, conditions so hostile that even extremophile organisms would struggle to survive. The discovery of these worlds provides a grim preview of what life might face in our own solar system had Jupiter achieved stellar ignition. But the biological challenges extend far beyond simple radiation damage or temperature extremes. The fundamental biochemical processes that enable life to grow, reproduce and evolve would be disrupted in ways that could prevent the emergence of complex organisms entirely. Consider the process of protein folding, by which long chains of amino acids twist and bend into the precise three-dimensional shapes that enable them to function as enzymes, structural components, and signaling molecules. Protein folding is exquisitely sensitive to temperature. Too cold, and proteins fold too slowly to maintain cellular functions. Too hot, and they unfold entirely, losing their biological activity. The extreme temperature swings in a binary star system would constantly denature proteins, requiring organisms to expend enormous amounts of energy, continuously rebuilding their molecular machinery. The problem becomes even more severe when we consider the complex biochemical pathways that enable organisms to reproduce. DNA replication, the process by which genetic information is copied and passed to offspring, requires a carefully orchestrated sequence of enzymatic reactions that must occur within narrow temperature and chemical ranges. The chaotic environmental conditions in a binary system would disrupt these delicate processes, making reproduction unreliable and preventing the stable transmission of genetic information that evolution requires. Even if some primitive organisms managed to survive and reproduce under such conditions, the development of complex multicellular life would face nearly insurmountable obstacles. Multicellularity requires precise coordination between different cell types, with complex signaling systems that enable cells to communicate and coordinate their activities. These signaling pathways typically depend on specific chemical gradients and electrical potentials that would be constantly disrupted by the extreme and unpredictable environmental conditions. The evolutionary pressures in a binary star system would favour only the most primitive and robust forms of life, instead of the progressive increase in complexity that characterised evolution on Earth, from simple bacteria to complex multicellular organisms to intelligent life. Evolution in a binary system would be dominated by survival strategies that prioritise resilience over sophistication. Organisms would need to devote most of their energy to simply maintaining basic cellular functions under constantly changing conditions, leaving little resources available for the development of complex structures or behaviours. Circadian rhythms, those internal biological clocks that synchronize cellular processes with the day-night cycle, would become meaningless in a world where the length and intensity of days vary unpredictably. Most life on Earth, from bacteria to humans, depends on circadian regulation to coordinate everything from cellular metabolism to reproductive cycles. The complex light patterns in a binary star system would make it impossible for organisms to maintain synchronized internal clocks, disrupting fundamental biological processes that depend on precise temporal coordination. The development of sensory systems would face equally daunting challenges. Eyes evolved on Earth to detect the specific wavelengths of light emitted by our Sun, with different species adapted to particular portions of the electromagnetic spectrum. In a binary system, organisms would need to process light from two different stellar sources, each with its own spectral characteristics that change as the stars move through their orbital dance. The complexity of developing visual systems capable of functioning under such variable conditions might prevent the evolution of sight entirely. Even more fundamentally, the chaotic environmental conditions would disrupt the stable ecological relationships that enable complex ecosystems to develop. Predator-prey relationships, symbiotic partnerships, and competitive interactions all depend on relatively predictable environmental conditions that allow species to co-evolve specialized adaptations. The constant environmental upheaval in a binary system would prevent the long-term stability needed for such relationships to develop and persist. The fossil record on Earth reveals that even relatively minor environmental changes can trigger mass extinctions that eliminate vast numbers of species and reset evolutionary progress. The Permian Triassic extinction, which eliminated over 90% of marine species 252 million years ago, was likely triggered by massive volcanic eruptions that altered global climate patterns for just a few thousand years. In a binary star system, such dramatic environmental changes would occur continuously, preventing life from ever establishing the stable ecosystems needed for evolutionary innovation. Perhaps most disturbing of all is the realization that intelligence, the emergence of consciousness and technological capability that has enabled humans to understand and manipulate their environment, would be nearly impossible under such conditions. Intelligence requires enormous energy investment in complex neural structures, long developmental periods during which young organisms learn and adapt, and stable social structures that enable knowledge to be accumulated and transmitted across generations. The chaotic conditions in a binary star system would make such investments in intelligence evolutionarily unfeasible. Any energy devoted to developing complex brains would be better spent on immediate survival needs. The unpredictable environment would make learned behaviors useless, as strategies that work during one environmental phase would be catastrophically inappropriate during the next. Social structures would be impossible to maintain when the basic requirements for survival change unpredictably over timescales shorter than individual lifespans. As we contemplate the biological implications of life in a binary star system, a profound realization emerges: the stable, single-star environment that enabled life on Earth to evolve from simple chemical reactions to complex ecosystems, and ultimately to consciousness itself, may be far rarer in the universe than we ever imagined. The countless binary star systems scattered throughout our galaxy may host worlds, but they are unlikely to nurture the patient, gradual development of complexity that made possible everything from the first photosynthetic bacteria to the human civilizations that now contemplate their place in the cosmos. But the implications of Jupiter's near-stellar transformation extend far beyond the biological challenges that individual organisms might face. The very architecture of our cosmic neighborhood would have been reshaped in ways that would reverberate through billions of years of solar system evolution. Beyond the orbit of Neptune, in the frozen twilight realm where sunlight barely penetrates, lies a vast sphere of icy debris that defines the outermost boundary of our solar system's gravitational influence. The Oort cloud, stretching nearly halfway to the nearest star, contains trillions of comets, locked in slow, stately orbits that take millions of years to complete. These pristine remnants of our solar system's birth represent the farthest extent of the Sun's dominion, a spherical shell of frozen material that serves as both archive and guardian of our cosmic origins. But in a universe where Jupiter had achieved stellar ignition, this magnificent structure would never have formed. The gravitational chaos unleashed by two stars locked in orbital combat would have scattered these primitive building blocks across interstellar space, depriving our solar system of its most distant sentinels and fundamentally altering the long-term evolution of planetary worlds. The Oort cloud's formation required billions of years of patient gravitational sculpting. As Jupiter and the other giant planets settled into their current orbits, following the chaotic early epochs of solar system formation, their gravitational influence gradually shepherded countless icy planetesimals into the distant regions where they could orbit undisturbed. This process, known as the Neis model, explains how the outer solar system achieved its current stable configuration through a complex dance of gravitational interactions that ejected some objects to interstellar space while preserving others in distant stable orbits. In a binary star system, this delicate process would have been impossible. The complex gravitational field created by two massive stellar objects would have prevented the formation of any stable reservoir of comets in the outer regions. Instead of the spherical shell of the Oort cloud, with its population of long-period comets that occasionally venture inward to grace our skies with their spectacular tails, the outer solar system would be essentially empty, a gravitational wasteland swept clean by the competing influences of two stars. The absence of long-period comets would have profound implications for the development of life on any surviving planets. Throughout Earth's history, cometary impacts have delivered crucial volatile compounds, water, organic molecules, and noble gases that helped shape our planet's atmosphere and oceans. The late heavy bombardment, that period of intense cometary impacts that occurred roughly 4 billion years ago, may have been essential for establishing the chemical conditions that allowed life to emerge. Without the Oort cloud as a source of these life-building materials, any surviving worlds in a binary system would be chemically impoverished, lacking the diverse inventory of compounds that enabled biochemical evolution on Earth. The transformation would extend throughout the entire architecture of the outer solar system. The Kuiper Belt, that flattened disk of icy bodies beyond Neptune's orbit that includes Pluto and thousands of other dwarf planets, would have been completely disrupted by the gravitational perturbations of a binary star system. Instead of the relatively stable collection of objects we observe today, each following predictable elliptical orbits that can be calculated centuries in advance, the trans-Neptunian region would be a chaotic zone of debris on highly unstable trajectories. Some Kuiper Belt objects would be flung into the inner solar system on collision courses with any surviving planets, while others would be ejected entirely from the solar system, joining the population of rogue planets that wander through interstellar space. The spectacular ring systems that grace the giant planets, Saturn's magnificent bands of ice and rock, the fainter rings of Jupiter, Uranus, and Neptune, would be constantly disrupted by gravitational perturbations, preventing the formation of the stable, long-lived structures we admire today. Perhaps most dramatically, the moons of the outer planets would face existential challenges that would reshape our understanding of where life might emerge in the solar system. Europa, with its subsurface ocean heated by tidal forces from Jupiter's gravity, represents one of the most promising targets in our search for extraterrestrial life. The delicate balance of tidal heating that keeps Europa's ocean liquid depends on the precise gravitational relationship between Jupiter, Europa, and its neighbouring moons, Io and Ganymede. In a binary star system, these orbital resonances would be constantly disrupted by external gravitational perturbations, either freezing Europa's ocean solid or heating it to the point where the Moon's icy shell would melt away entirely. Titan, Saturn's largest moon, and the only body in our solar system other than Earth with stable liquid on its surface, would face equally dire prospects. The thick nitrogen atmosphere and methane lakes that make Titan such a fascinating world depend on the Moon's stable orbit around Saturn and the consistent heating provided by radioactive decay in its interior. The gravitational chaos of a binary system would likely strip away Titan's atmosphere and disrupt the delicate chemistry that creates its complex organic compounds, eliminating what may be our best example of prebiotic chemistry occurring elsewhere in the solar system. The implications extend far beyond our own solar system to our understanding of planetary formation throughout the galaxy. The discovery of thousands of exoplanets over the past 3 decades has revealed that planetary systems come in an astonishing variety of configurations, many of which bear little resemblance to our own solar system's orderly arrangement. Hot Jupiters orbiting closer to their stars than Mercury orbits our Sun, super-Earths with no analogue in our solar system, and planets on highly eccentric orbits that carry them from scorching proximity to frozen exile. All of these exotic worlds have forced astronomers to revise their theories of how planetary systems form and evolve. But the discovery of planets in binary star systems has provided perhaps the most dramatic challenge to our understanding of planetary formation. Kepler-47, a system containing 2 stars and at least 3 planets, demonstrates that complex planetary systems can indeed form and survive in binary environments. Yet the planets in such systems tend to be either very close to one of the stars, where they can maintain stable orbits within that star's gravitational dominance zone, or very far from both stars, where they orbit the entire binary system as a single gravitational unit. The intermediate regions, the zones where Earth, Mars and Venus orbit in our solar system, appear to be largely devoid of stable planets in binary systems. This observation supports the theoretical predictions that emerged from our exploration of Jupiter's near-stellar evolution. The gravitational chaos created by 2 stars makes it nearly impossible for planets to maintain stable orbits in what we might consider the habitable zone of such systems. The rarity of Earth-like planets in binary systems has profound implications for the search for life elsewhere in the galaxy. Binary and multiple star systems comprise perhaps 60% or more of all stellar systems in our galaxy, meaning that the majority of stars exist in gravitational environments that are hostile to the formation of stable, temperate worlds. If complex life requires the kind of stable single-star environment that enabled Earth's biosphere to develop over billions of years, then habitable worlds may be far rarer in the cosmic context than optimistic estimates of the Drake equation have suggested. This realization transforms our perspective on the Fermi paradox, the apparent contradiction between the high probability of extraterrestrial life, suggested by the vast number of stars and galaxies, and the lack of evidence for such life that we observe. If the majority of stellar systems are binary, or multiple star configurations that prevent the formation of stable, habitable worlds, then the Great Filter that prevents the emergence of technological civilizations may not be some catastrophic event that destroys advanced species, but rather the simple rarity of stable planetary environments where complex life can evolve in the first place. The anthropic principle, the observation that the universe appears to be fine-tuned for the existence of conscious observers, takes on new significance in this context. We exist not simply because the fundamental constants of physics happen to allow for the formation of stars, planets, and complex chemistry, but because we happen to reside in one of the minority of stellar systems where planetary formation could proceed along stable, predictable lines. The failure of Jupiter to achieve stellar ignition was not merely a local astronomical event, but a cosmic lottery whose outcome determined whether our solar system would join the ranks of chaotic binary systems or remain in the smaller population of stable, single-star environments where life can flourish. The long-term evolution of binary star systems also presents challenges that would affect habitability over cosmic timescales. As binary stars age and exhaust their nuclear fuel, they undergo complex evolutionary processes that can dramatically alter their luminosity and stellar wind output. When one star in a binary pair evolves into a red giant, it can transfer mass to its companion, triggering nova explosions or even Type Ia supernovae that would sterilize any planets within dozens of light years. The stable, predictable stellar evolution that has allowed our Sun to maintain relatively constant energy output for billions of years, the kind of stability that complex life requires, is much rarer in binary systems where stellar interactions can trigger dramatic changes in luminosity over much shorter timescales. Even the formation of heavy elements that are essential for rocky planets and biological chemistry would be affected in a universe dominated by binary star evolution. The nucleosynthesis processes that create elements like carbon, oxygen, silicon and iron depend on specific conditions within stellar cores and during supernova explosions. Binary star evolution can alter these processes, potentially changing the relative abundances of heavy elements in ways that would affect the composition of planets and the chemistry available for biological evolution. The cosmic perspective also reveals how Jupiter's near-stellar transformation would have affected our understanding of the galaxy itself. Much of our knowledge about stellar evolution, planetary formation, and astrobiology has been shaped by detailed observations of our own solar system, which serves as the primary laboratory for testing theories about how planetary systems work. Had Jupiter become a star, our solar system would have been a binary system, and our scientific understanding would have been biased toward the assumption that chaotic, unstable planetary environments are the norm rather than the exception. This altered perspective would have profoundly affected our search for life elsewhere in the galaxy. Instead of looking for planets in stable, circular orbits around single stars, the kind of environment that we know can support complex life, we might have assumed that life must be adapted to the chaotic conditions of binary systems. Our CT searches would have focused on detecting signals from civilizations that had somehow managed to develop technology despite the environmental chaos of binary star systems, rather than recognizing that such civilizations might be essentially impossible. The philosophical implications are equally profound. The Copernican revolution displaced Earth from the center of the universe, while the modern understanding of cosmic evolution has revealed that we occupy no special position in space or time, but the realization that stable single-star systems may be the exception rather than the rule suggests that Earth's environment may be far more remarkable than we previously understood, not because of our location in the galaxy, but because of the specific sequence of events that created the stable conditions under which complex life could evolve. As we peer deeper into the cosmos with increasingly sophisticated telescopes and detection methods, we are beginning to appreciate just how many factors had to align precisely to create the stable, life-supporting environment we inhabit. The failure of Jupiter to achieve stellar ignition represents just one crucial element in a chain of cosmic coincidences that enabled our existence. Yet perhaps the most unsettling realization is not that we are alone in a chaotic universe, but that we may be among the fortunate few worlds where the cosmos conspired to create islands of stability in an ocean of gravitational chaos. The story of what might have been, a solar system with 2 stars and no stable refuge for the patient development of life, serves as a mirror that reflects back the extraordinary nature of what actually is. But as we contemplate these cosmic scales and the vast sweep of stellar evolution, we must confront one final, haunting question about our place in a universe where such remarkable stability may be far more fragile than we ever dared to imagine. In the summer of 2016, the Juno spacecraft entered orbit around Jupiter after a 5-year journey across the solar system, carrying instruments designed to peer beneath the gas giant's swirling clouds and into the heart of our solar system's most enigmatic world. As Juno's sensors probed Jupiter's interior with unprecedented precision, they revealed something unexpected. The planet's core was not the solid, well-defined sphere that astronomers had long envisioned, but rather a diffuse, partially dissolved structure that spoke of a violent and chaotic formation process. The implications of this discovery ripple backward through time to those crucial epochs 4.6 billion years ago, when Jupiter was racing toward potential stellar ignition. Computer models based on Juno's data suggest that Jupiter may have experienced massive collisions with other planetary embryos during its formation. Cosmic impacts that release so much energy, they partially melted the growing planet's core and brought its interior temperature even closer to the threshold needed for nuclear fusion. How close did Jupiter actually come to becoming a star? The answer lies in a margin so narrow it defies comprehension. Current estimates suggest that Jupiter would have needed to accumulate approximately 75 times its present mass to achieve the sustained deuterium fusion that marks the boundary between planet and brown dwarf star. In the context of the early solar system's total mass budget, this represents less than 8% of the material that was available in the primordial disk. Put another way, had the gravitational dynamics of the forming solar system been altered by just a few percentage points, slightly higher density in Jupiter's feeding zone, a delay of merely 1 million years in Saturn's formation, or a marginally different distribution of angular momentum in the collapsing nebula, our gas giant might have crossed that critical threshold. The razor-thin nature of this margin becomes even more unsettling when we consider recent discoveries of other failed stars throughout the galaxy. Brown dwarfs, those intermediate objects that fall between planets and true stars, are far more common than astronomers once believed. The nearest known brown dwarf, Lumen 16, lies just 6.5 light-years from Earth, practically next door in cosmic terms. This binary system of two brown dwarfs, each roughly 30 to 60 times Jupiter's mass, represents what our solar system might have become had Jupiter's accretion process continued for just a few million years longer. Perhaps even more disturbing are the discoveries of planetary systems, where gas giants did achieve stellar ignition. The TRAPPIST-1 system, with its 7 Earth-sized planets orbiting an ultra-cool dwarf star, may represent an alternate evolutionary pathway where a Jupiter analogue successfully ignited and became the system's primary star. The 7 worlds of TRAPPIST. One experienced the kind of complex orbital dynamics and tidal interactions that Earth might have faced in a binary system, though in this case the failed Jupiter became the system's only star rather than a secondary companion. These observations force us to confront an uncomfortable truth. The stable, single-star architecture that enabled life on Earth may represent a cosmic accident of extraordinary rarity. As we catalogue more and more exoplanetary systems, we're discovering that chaotic, unstable configurations, hot Jupiters spiralling into their parent stars, planets on wildly eccentric orbits, binary systems with complex gravitational dynamics, are far more common than systems like our own. The Kepler Space Telescope and its successor, TERS-S, have revealed that planetary systems exhibit an almost bewildering diversity of configurations, yet Earth-sized planets in stable, circular orbits around Sun-like stars remain stubbornly rare in the observational data. This could be due to detection biases. Our instruments are better at finding large planets on short-period orbits, but mounting evidence suggests that truly stable, habitable environments may be genuinely uncommon in the galaxy. Consider the recently discovered TOI 715 system, where a potentially habitable planet orbits a red dwarf star. The planet experiences tidal forces that likely keep one hemisphere permanently facing its star while the other remains in eternal darkness, a configuration that Earth might have experienced had it been captured in a close orbit around our Sun in a hypothetical binary system. While such worlds might theoretically support life in their twilight zones, they bear little resemblance to the temperate dynamic environment that enabled Earth's biosphere to flourish. The anthropic principle, the observation that the universe's fundamental constants appear fine-tuned for the existence of conscious observers, takes on profound new meaning in this context. We exist not only because the laws of physics permit the formation of stars, planets, and complex chemistry, but because a series of extraordinarily improbable events conspired to create one of the universe's rare islands of gravitational stability. The list of cosmic coincidences required for our existence extends far beyond Jupiter's failed stellar ignition. The Moon's formation through a giant impact that left Earth with exactly the right rotational period and axial tilt for climate stability. The precise timing of the late heavy bombardment that delivered water and organic compounds without sterilizing the planet. The emergence of plate tectonics that recycled carbon and maintained global temperatures within habitable ranges. The evolution of photosynthesis that transformed Earth's atmosphere and enabled complex life. Each of these events required specific conditions that could easily have unfolded differently. Had Jupiter achieved stellar ignition, none of them could have occurred as they did. the stable climate that enabled the gradual evolution of life over billions of years would have been replaced by chaotic swings between freezing and scorching conditions. The Moon might never have formed, depriving Earth of the tidal forces that may have been crucial for the emergence of life from primordial oceans. The careful balance of atmospheric composition that maintains liquid water on Earth's surface would have been disrupted by the complex heating patterns of binary illumination. Yet perhaps the most profound implication concerns the search for intelligence elsewhere in the universe. The Drake equation, which attempts to estimate the number of communicating civilizations in our galaxy, has traditionally focused on factors like the rate of star formation, the fraction of stars with planets, and the likelihood of life emerging on suitable worlds. But the recognition that stable planetary environments may be far rarer than previously assumed adds a new term to this equation, one that dramatically reduces the probability of technological civilizations arising anywhere in the cosmos. Intelligence requires not just the emergence of life, but its patient evolution over billions of years through increasing levels of complexity. Single-celled organisms must evolve into multicellular creatures, develop complex nervous systems, achieve consciousness, and ultimately develop the technological capability to communicate across interstellar distances. Each step in this progression requires stable environmental conditions maintained over geological timescales, exactly the kind of stability that binary star systems cannot provide. The Fermi paradox, the apparent contradiction between the high probability of extraterrestrial intelligence and our failure to detect any evidence of such civilizations, may find its resolution not in some catastrophic, great filter that destroys advanced civilizations, but in the simple rarity of stable environments where intelligence can evolve in the first place. The vast majority of stellar systems in our galaxy may be gravitational chaos zones where consciousness never has the chance to emerge from the primordial soup of basic chemistry. This realization casts our own existence in a sobering new light. We are not merely the products of biological evolution on a hospitable planet, but the beneficiaries of a cosmic lottery whose odds make winning the jackpot seem like a certainty by comparison. Every sunset we witness, every breath of oxygen we draw, every thought we think exists because Jupiter fell just short of stellar ignition 4.6 billion years ago. The implications extend to our responsibilities as potentially one of the universe's rare conscious civilizations. If stable, life-supporting environments are as uncommon as these considerations suggest, then Earth may represent something far more precious than we ever imagined, not just our home, but perhaps one of consciousness's few footholds in a largely chaotic cosmos. The environmental challenges we face today, from climate change to habitat destruction, take on cosmic significance when viewed against the backdrop of how rare habitable worlds may truly be. Recent advances in astrobiology have begun to quantify just how narrow the range of conditions suitable for life may be. The concept of the habitable zone, the range of distances from a star where liquid water can exist on a planetary surface, has been refined to account for atmospheric composition, greenhouse effects, and stellar variability. When all factors are considered, the zone where Earth-like conditions can persist over billions of years shrinks to a remarkably narrow range around Sun-like stars. In binary star systems, this habitable zone becomes even more constrained, if it exists at all. The complex orbital dynamics that would have characterized Earth's motion in such a system would carry our planet alternately closer to and farther from the binary pair, causing dramatic temperature swings that would push conditions outside the narrow range where complex life can thrive. The stable climate that has enabled Earth's biosphere to evolve gradually over geological time would be replaced by chaotic variations that would repeatedly reset any evolutionary progress. The geological record on Earth reveals just how sensitive life is to environmental changes. The 5 major mass extinctions in Earth's history were triggered by events far less dramatic than the constant climate chaos that would characterize a binary star system. The Permian Triassic extinction, which eliminated over 90% of marine species, was caused by volcanic eruptions that altered global temperatures by just a few degrees for a few thousand years. In a binary system, such temperature variations would occur continuously, preventing the establishment of stable ecosystems where complex life could evolve. As we push the boundaries of our search for extraterrestrial intelligence, scanning the cosmos for radio signals or other signs of technological civilizations, we must grapple with the possibility that we are conducting a largely futile quest. If the emergence of consciousness requires the kind of stable, single-star environment that produced Earth, then the universe may be filled with binary star systems hosting worlds where life never progressed beyond the most primitive stages. The recently launched James Webb Space Telescope and other next-generation instruments will soon provide unprecedented insights into the atmospheres of exoplanets, allowing us to search for biosignatures, chemical evidence of life, on distant worlds. But the harsh reality may be that most planets exist in gravitational environments too chaotic to support the stable atmospheric chemistry that produces detectable biological signatures. The search for life may ultimately reveal not a cosmos teeming with biological activity, but a universe where consciousness represents an almost impossibly rare emergence from the background of cosmic chaos. We may be among the precious few worlds where the gravitational dice happen to fall in just the right configuration to allow intelligence to bootstrap itself from the fundamental laws of physics into self-aware contemplation of its own existence. Standing beneath Jupiter's glow in our night sky, knowing what we now know about its near-stellar nature and the razor-thin margin that separated us from cosmic chaos, we confront a truth both humbling and terrifying. We are not the inevitable result of cosmic evolution, but the products of an almost infinitely improbable sequence of events that could easily have unfolded differently. Every moment of our existence is borrowed time, made possible by a failed star that came tantalizingly close to rewriting the story of our solar system. The universe may be vast beyond imagination, filled with hundreds of billions of galaxies each containing hundreds of billions of stars. But if stable, life-supporting environments require the kind of cosmic lottery that produced our solar system, then consciousness may be far lonelier in this vast expanse than our most pessimistic estimates have ever suggested. In the end, Jupiter's failure to become a star may represent not just the key to our existence, but the explanation for our cosmic solitude. In a universe where the vast majority of worlds exist in gravitational chaos zones hostile to the patient development of complexity, we may be among the precious few islands of stability where the cosmos has managed to know itself through conscious observation. And that perhaps makes every sunrise, every breath, every thought we think infinitely more precious than we ever dared to imagine. In the vast darkness between the stars, how many worlds like ours never had the chance to bloom, because their Jupiter succeeded where ours failed?